Welcome to probability, the JC side of probability. Now, before we jump right into this, you have to be familiar with the concepts and some of the terms that we actually discussed in the earlier chapter called permutation and combination. So make sure to go and revise that if you have not, because some of the concepts that we use there will be applied in this chapter as well. So this is the first video of the JT side probability, and we're going to start off by recapping some of the definitions that you have learned in the past in secondary school before. Now, it's been some time since we did probability. That's why it's important to go through these basic things before we actually jump right into the JC side of things. Right, so just treat this like a recap of whatever you learned in the past. Okay, so let's start off with a very broad idea of what probability is, right? Probability, or it just means what are the chances of something happening, right? To put it very bluntly. So I'm going to be using a very classic example to paint the picture to you, and also to use this classic example to run through the terms that you need to know. The definition. Okay, you don't need to know them word for word, but you need to know the meaning of the term. Okay, so let's say, in probability, everything starts with an experiment. So an experiment occurs. Now, this experiment is the first key term. So this experiment, let's say, I'm just gonna paint an example here. For example, is I roll a dice, right? I can roll a dice. So when I roll a dice, what happens? I will have many different possible outcomes, right? For example, let's say I have 1, 2, 3, 4, 5, 6. Now, this whole collection over here, or this whole set of all possible outcomes, is what we call our sample space. So if we want to write it in a more concise way, we can write 1, 2, 3, 4, 5, 6. So sample space is basically the set that contains all the different possible outcomes from an experiment. Okay, but we know that when you roll a dice, there can only be one possible outcome, right? So you can only get a 1 or you can only get a 2, right? You cannot roll a dice and then you get 1 and 2, right? So each outcome is unique. Now, that's it. Given that we have all these set of possible outcomes, right? Let's say I want an event. So let's say I want an event, which is basically all odd digits. So what is the probability that I get all odd digits? So you can see that this 1, this 3, and this 5, they are all odd digits, right? And an event is basically a subset of the sample space. So an event is basically a collection of a set of outcomes that are a part of the entire sample space, which means that, let's say I want to find the probability of all odd digits, right? We know that this over here, the sample space for all odd digits would be 1, 3, 5. So the probability of this happening would be the number of elements over here, which is 3 out of 6, right? And then you can see that these 3 outcomes over here, they are a subset of the sample space. So in my probability is half. Now, an event is a subset of the sample space. And given the definition of subset, an event can be the sample space. So we say that the event over here can be the sample space, right? So that's it. It means that the event can also technically be the whole sample space. For example, let's say I'll find the probability that I get a whole number, right? We realize that for me to get a whole number, 1, 2, 3, 4, 5, 6, all the criteria, right? And as a result, I have 6 possible outcomes, or 6 possible outcomes, and then 5, right? So just some final recap over here. For probability of any event, right? It will always be between 0 and 1. Okay, so that's the first most important thing. Now, if the probability is 0, we call this an impossible event, while this over here is called a definite event, or you can say it's a certain event, right? It definitely will happen, okay? And the second thing over here is the probability of an event is basically the number of outcomes that I want of the event over the sample space. So how many elements there are in the sample space is going to be in the denominator, and how many elements are there in the event space, that will be the numerator. Okay, so this is basically just a recap. I've not gone into any of the JC sub things here, but this is important to know. So now we can say, try this question now. Pause the screen right now to tackle this question and come, right? Because this question over here is a very good question to recap basics. And without further ado, I'm going to jump right in, so make sure to pause to do this. Now I'm going to go through the answer right now. So we have 2 ordinary pair dice, right? Find the probability that both dice show 6. Now, of course, in my earlier example over here, right, I've just went through all the basic definitions and all. But of course, you are expected to know some things as well. Okay, I'm just going to write it here. So you are expected to know these two things, which is my addition principle and my multiplication principle, right? So the addition principle comes from the keyword called or, and the multiplication principle comes from the keyword called and. So let's say I want the probability of apple or pear, right? Then this will be probability of apple plus probability of pear. Now, what if it's apple and pear, right? That means apple first, then pear. So this one will be probability of apple times probability of pear, right? To keep things very simple, right? Assuming independent events. So back to here, right? What's the probability that these two dice show 6? So the probability that dice 1 is 6 and dice 2 is 6. You realize that there's a keyword and over here, and therefore its probability of dice 1 is 6 and the probability of dice 2 is 6. And therefore it will just be 1 out of 6 times 1 out of 6. It gives me 1 out of 36 over here, right? Because we want both to be 6 and therefore it's an AND condition over there. So for the second one, both dice show the same number. So probability of both dice show the same number. So what are all the different possible cases, right? I have 1 1 or 2 2 or 3 3. You see, when I say or, I put a plus, right? Because we're adding them together. Mutually exclusive, we are adding them together. Now, 4 4, 5 5, and last but not least, 6 6, right? So you know that the probability of each individual one, this one over here would be 1 out of 6 times 1 out of 6. And then this one over here is just 1 out of 6 times 1 out of 6, right? And then it also repeats for every single probability case over there. And therefore, at the end, when we add up everything together, we will have 6 of 1 out of 6 times 1 out of 6, which is basically just 6 out of 36, which gives me 1 out of 6 in the end, right? So whenever I need all, we add them together, right? Because they are mutually exclusive. So this one is for mutually exclusive events over here. That's why we can add them together. Because in the Venn diagram, they don't overlap. And since they don't overlap, we can add the two probabilities together, right? Because we don't need to worry about any of the regions being repeated because they simply just don't overlap. Okay, so this is the first two. Now, the sum of the numbers on both dice. So for triple I over here, dice 1, dice 2, right? This is for triple I. If dice 1 is 3 and dice 2 is 5, we will get 8. If dice 1 is 5 and dice 2 is 3, we also get 8, right? If dice 9 is 4 and dice 2 is 4, we also get 8. Now, since both 4 are the same, we don't need to stop the position because 4 and 4 is the same thing, right? And last but not least, here's 2, here's 6, we get 8. And when here is 6 and here is 2, we also get 8. So in the end, we have 5 different pairings, 5 pairs. Or how many pairs in total? In total, we actually have 36 different pairs, right? So the probability for I would just be 5 out of 36, simply because we have 5 pairs that meet our criteria out of 36 pairs. Now, how do I rewrite the 36 pairs over here? It's because if you recall your permutations and combinations, right, I have 2 values here. The first one, I have 6 different options from the first dice, and then from the second dice, I have 6 different options. So give me 36 different pairs. As simple as that, right? 36 different pairs. And that's why over here it's 5 out of 36. All right. Now, IV, the sum of the numbers on both dice actually over here. So we want to be more than 8. Okay, so how do we actually do this in a systematic way? Actually, nice way to do this would be to actually draw a table. So I'm going to draw a table over here. Okay, this one is a method you can use for this type of questions, especially in between dice, right? Let's say dice 1, and then here's so the outcomes would be as such. So I draw a line here. Okay, so let's say here I have 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Then if I draw a line down like that, and then I draw a line across like that, you realize that they add up, right? So here's 2, 3, 4, 5, 6, 7, 3, 4, 5, 6, 7, 8, 4, 5, 6, 7, 8, 4, 5, 6, 7, 9, 5, 6, 7, 8, 9, 10, 6, 7, 8, 9, 10, 11, 7, 8, 9, 10, 11, 12. Right? When we add up them together. And if you want more than 8, right, you can see that it 9, 10, 11, 12. So 9 is all here. And they're all at the corner over here. Right? And if you count the number of different elements over there, there are 10 different elements here. So in total, the probability for IV would be 10 out of 36, which gives me 5 out of 18 over here. Because I've you can count that 10, I got 10 different entries that will fit my, what I want out of 36 different entries. That's why the answer over here is 5 out of 18, right, for IB. Okay? And last but not least, we have B, the number on the dice that differ by more than 2. So we can actually use this table over here again to help us figure out the numbers on the dice that differ by more than 2. So if let's say I physically enumerate everything, right? Okay, I'm going to use a highlighter for this example. Differ by more than 2. So for, let's say when this is 1 over here, what will actually be the criteria over here? Differ by more than 2. So that means it has to be 4, 5, 6 over here, right? 4, 5, 6, because 4 minus 1 is 3, and then 5 minus 1 is, 4. So for 2 over here, differ more than 2 means that it's 5 or 6 over here, right? Now for 3, differ more than 2, that means it's got to be over here. Now back to 4, differ more than 2 means that it has to be 1 only, because 4 minus 1 gives me 3. So here, and then 5, for die 1 number 5, right? Differ more than 2 means that it will either be 1 or 2. Right? Because 5 minus 2 is 3 and 5 minus 1 is 4. So you could either be these two, right? And the last one is for 6, right? Differ more than 2 means that the second dice could either be 1, 2, or 3. So 1, 2, or 3. Here. So if you count, right, for the last portion, part B, PD over here. PV. In total, I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 12 out of 26, which will give me a total value of 1 over 3 as the final answer. Okay, so for dice questions, just as a tip, in case in the future you actually encounter them again, it'll be a lot better for you to go and physically enumerate all the different possible outcomes. And by drawing a table like that, it makes things very, very easy. Okay, any questions, let me know in the comments below. Otherwise, I'll see you in the next video to actually start going through the concepts involving Venn diagrams over here, and I'll see you.